Hello friends, in this video we are going to learn about the packing efficiency, that what it means and how it is important and what are the various factors that affect packing efficiency. Let me tell you one thing first, that this packing efficiency topic is very important in engineering metallurgy subject and all the materials related subject. So let's see without wasting time. So what do you mean by packing efficiency? First I want to tell you is that what is the definition of packing efficiency and what it means actually. Please see, the packing efficiency is the fraction of the crystal or unit cell actually occupied by the atoms. Please see, it is nothing but what? It is the fraction of the crystal or unit cell actually occupied by the atoms. Okay, actually occupied by the atoms. It means it is nothing but the volume occupied by the crystal into the unit cell. Okay, then it must always be less than 100%. See guys, it must always be less than 100% because it is impossible to pack spheres. Okay, because it is impossible to pack spheres, that is atoms are usually spherical. That is why I have used the word spheres. You can see I am repeating, please must pay your attention. It must always be less than 100% because it is impossible to pack spheres without having some empty space between them. Okay, because why this spheres word is used there? Because atoms are usually spherical. If you can see the bracket, in bracket it is written there that atoms are usually spherical. So if you pack some spheres, you can do at your home also this kind of experiment. If you have taken so many balls and if you are going to pack it in a in a box, small box, so you may observe that it is very impossible, it is clearly impossible to pack spheres without leaving some empty spaces in between them, because spherical structures, crystals or spheres are always packed with some empty spaces. That is why they are always less than 100%. Okay, so packing efficiency is the fraction of the crystal or unit cell actually occupied by the atoms, and it must always be less than 100%. And you know why it is less than 100%? Because it is impossible to pack spheres, that is atoms, because atoms are usually in spherical shape, without having some empty space between them. Okay, now in this slide you can see I am bringing you some of the spheres diagram, that how it is looks. You can see atoms are looking like that. Okay, all these images that you are seeing here. Okay, so that atoms are spherical in shape. You can see these are spherical, completely spherical in shape, and that because they are spherical in shape, it is impossible to pack them without leaving some space in between them. Okay, so you can see here at hexagonal closely pack, and then again this structure, then again this cubic close pack structure, that how they are packing or how they are occupying the space. You can see here some space are left by while packing of that atoms. You can observe there. Okay, you can observe this phenomena in this diagram itself. Now how you can express the packing efficiency mathematically? Okay, that is why one numerical formula that you are seeing, that mathematically packing efficiency is, okay, it is written that mathematically packing efficiency is, so how it is given: the number of atoms into volume occupied by one share into 100 divided by total volume of unit cell. Okay, it is always expressed in percent. Okay, packing efficiency is always expressed in percent, we know that. So let's see, I am repeating: number of atoms into volume occupied by one share multiplied by 100 divided by total volume of unit cell. Okay, so it is nothing but the volume occupied by an atom in an unit cell and divided by total volume of unit cell. This is what the definition or mathematical relation for calculating packing efficiency. So guys, let's see that each and every crystal structure has different packing efficiency, and in this video we are going to see how to calculate it. Okay, please see. First we should understood that what are the various factors that affect the packing efficiency. Please see, following factors define packing efficiency of unit cell. first of all, volume of unit cell. Okay, so this volume of unit cell is affected to define the packing efficiency. Then second one is number of items in a structure. How many number of items are there in your structure, that also important to define packing efficiency. And then volume of atoms. Okay, then volume of atoms. Now see, all of you must see that these factors, that is volume of unit cell, number of atoms in a structure, and volume of atoms, these three factors are mainly responsible or mainly helpful or important to define the packing efficiency of unit cell. So this helps you while remembering the definition of packing efficiency. You can focus on these three factors, okay, or parameters. Now let's move forward towards the different crystal structures and how to calculate the packing efficiency for different crystal structures. Please see. Now you can see packing efficiency for simple cubic lattice. Okay, I have given heading. You can observe here packing efficiency of simple cubic lattice. So how to calculate the packing efficiency of simple cubic lattice? Please see. In a simple cubic lattice, the atoms are located only on corners of the cube. See guys, there is, if we have seen in previous videos that BCC is a crystal lattice, then FCC and HCP. So BCC crystal lattice, what it contains each atom at the corner of a cube and one atom at the center of cube. But in case of simple cubic lattice, we know that the atoms are located only on the corners of the cube, not on the center of cube. So that is why from given figure we can see that particles are in touch only at the edges. You can see on this diagram. Okay, we can clearly observe on this diagram that what particles are in touch only at the edges. Okay, particles are touch only at the edges of this diagram, we can observe. So what is the formula for packing efficiency is, therefore we have written here packing efficiency is equals to, you can see packing efficiency is equals to volume of one atom divided by volume of cubic unit cell into 100. Okay, volume of one atom. Why it is written one atom? Because it is, we can see that the particles are touch only at the edges itself. So volume of one atom divided by volume of cubic unit cell multiplied by 100. Now we have seen in the definition of packing efficiency that atoms are generally in a spherical shape. It means they are spheres. Now what are the formula for volume of spheres? That is 4/3 pi r cube. You can, we have know this, we have know it very well. The relation for calculating the volume of sphere is 4/3 pi r cube. So that is why volume of an atom, then we know that atom is a sphere, because at all atoms, usually atoms are having a spherical shape. So that is why what we did here, volume of one atom is 4/3 pi r cube, 4/3 pi r cube divided by volume of cubic unit cell, cubic, that is why 8r cube, then multiplied by 100, because efficiency is always expressed in percentage. That is why we have to multiply it by 100. Then what we left with, if you calculating this relation, then what we are left with, pi by 6 into 100, and if you calculate the value for that, so pi by 52.36% or 52.4% is the packing efficiency for simple cubic lattice or simple cubic lattice structure. Now let's see what is next. The next is packing efficiency for, you can see, body centered cubic structure. Now what is the packing efficiency for body centered cubic structure? Please see. Okay, packing efficiency for body centered cubic structure. So in body centered cubic structure, the three atoms are diagonally arranged. We know that. You can see three atoms are diagonally arranged. You can see here. To find the packing efficiency, we consider a cube with edge length, face diagonal length B and cube diagonal as C. I am reading it once again. To find the packing efficiency, we consider a cube with edge length A, face length B and cube diagonal as C. Edge length is denoted by A, then face diagonal denoted by B and cube diagonal as C. Okay, so what is the formula for packing efficiency? Volume occupied by two spheres in the unit cell. Why two spheres? Because in BCC we can see each corner atoms, okay, touches to their adjoining atom. Okay, then this is A, then B, then C. Then by using Pythagoras theorem we can see 4 by 3 pi r cube into 100 divided by 4 by under root 3 into r raised to the power 3. So we are left with this, and if we calculating this total value, then we are left with the 68%. So if by this relation and by this calculation, the packing efficiency of body centered cubic structure is 68%. Okay, now what about FCC? So this packing efficiency for FCC, now see. So packing efficiency for face centered cubic. Now you can see this, there are 3 spheres we can see, and these 3 spheres are touches with each other, because in FCC crystal structure we know that the center atoms touches to the corner atoms. This is the condition for FCC. So packing efficiency for FCC is 4 atoms multiplied by volume per atom divided by volume of unit cell multiplied by 100. So we have 4 into 4 by 3 pi r cube upon 2 root 2 into r cube into 100. So if you calculate all this relation, and this 2 root 2 value we are taken is from here, because edge radius is 2 under 2 by radius is denoted by r multiplied by 100. So we are calculating, if we have calculated this packing efficiency of face centered cubic structure, then we are left with the 74%. So in this video, by this all relation, we get to know that the packing efficiency for simple cubic lattice is 52.4%. Packing efficiency for BCC, that is body centered cubic structure, is 68%, and the packing efficiency for face centered cubic structure is 74%. I hope this content may help you to understand what do you mean by packing efficiency and how to calculate packing efficiency for SCC, BCC, FCC all. Okay, thank you.